All right. Good morning or good afternoon, everyone. Thank you for joining us today. Welcome to our webinar, part of the SZ4D International Webinar Series. I'm Anaïs Ferraud. I am the SZ4D Managing Director, and I'll be your host today. Before we begin, just a few housekeeping notes. We have live translated closed captions available for you at the bottom of your screen if needed. You are also welcome to submit your questions using the Q&A feature, and we will address those questions after the presentation. Today's webinar is being recorded, and it will be available on our SZ4D YouTube channel, where you can also find recordings from all of our previous presentations. So it's my pleasure to introduce today's speaker, Jonathan Delph, Assistant Professor at Purdue University. John's research focuses on developing and applying advanced seismic imaging techniques to create high-resolution images of the Earth's crust and the uppermost mantle. Today, John will discuss lateral variations in geophysical, seismogenic, and tectonic features along the Cascadia Forearc. John, thank you so much for joining us today. Take it away.
Yeah, thanks, Anaïs, and thank you to everyone for being here today. Also, thank you to the SZ4D for allowing me to share some research we've been doing in this region for about the past 9 years or so, trying to understand how lateral variability in the manifestation of subduction along the Cascadia margin could be connected. There's a lot of different features that seem to correlate in Cascadia, and what we're really after is trying to understand that are driving these correlations. One that Cascadia is particularly well known for is episodic slow slip and non-volcanic tremor. It's plotted here on the bottom. We think this is a process that is fluid mediated and occurs at the plate interface from depths from about 20 to 50 kilometers down or so. But this process is also heterogeneous along the strike of the margin. You can see high amounts of non-volcanic tremor in southern and northern portions of Cascadia and relatively muted in central Cascadia. And this correlates with some other features as well. Up here, I've plotted forearc topography, where we see that we have elevated forearc domains in these regions that experience higher amounts of non-volcanic tremor density. These are not the only things that correlate, and I'll talk a little bit about other ones as well. But again, this focus is really trying to understand from either some physical process or a mechanistic way how these different variations can be linked together. So a quick outline of this talk, I'll go over a brief introduction of how we got to the modern Cascadia subduction margin, how fluids are generally expressed in subduction zones, because we think that a lot of the processes that we're looking at today are tied to the presence of fluids, and what other lateral variations exist in Cascadia. Because this is a pretty multidisciplinary audience, I'm not going to focus too much on the details of how we go about building these. Briefly touch on the techniques that we use for building these 3D models of the crust and uppermost mantle structure. And then I want to focus on two major topics in this talk, relating the shear wave velocity structure that we see along the margin to subduction processes, and then linking that to surface uplift features, things like topography. Of course, in order to gain insight into these, we need to have some model that is sensitive to the depth range over which the structures that link these things are operating. And by the end of the talk, I'd like to convince you that I think a lot of the lateral variations in Cascadia can be linked together through a process called basal accretion, or the transference of material from the downgoing to the overriding plate. And we think that the presence of fluids makes this process much more efficient. Okay, so the Cascadia margin, as we see it today, is a relatively long-lived subduction system. It's been operating since the accretion of the which is a over-thickened oceanic plateau-like crust that was accreted onto the margin about 50 to 55 million years ago. Prior to the accretion of the Silesia terrain, we had subduction further inboard in the North American continent, and that subduction jumped out to its current location after accretion. The southern portion of the Forearc is a little different. It comprises the Klamath terrain, which is kind of older accreted terrains, largely oceanic island arc rocks and oceanic crust within it. The downgoing plate is pretty young along the margin, about 10 million years old at the oldest near the trench, younging to about 5 million years in either direction. So not a lot of variability in downgoing plate age. And it subducts at kind of an intermediate rate compared to global subduction zones, about 40 millimeters per year on average. And these latter two bullets are really important because it makes Cascadia one of our warm subduction globally. And what this implies is that we release water from our downgoing oceanic lithosphere at really shallow depths, about as shallow as we can get for that eclogite transition of about 40 kilometers. And what that means is that the fluids that are released can actually affect the behavior of the plate interface and be reflected in different processes associated with that. So I want to stress that these fluids are being released from metamorphic dehydration reactions. These are not fluids that are coming out of things like pore space closure and sedimentary rocks. We think that happens at pretty shallow depths, shallow in about 10 kilometers. So these are taking hydrous mineral assemblages within our downgoing oceanic lithosphere, taking them down to PT conditions where they become unstable and then undergo a reaction that releases water, and they're left with an anhydrous mineral component instead. So we think that this is mechanically manifest through intraslab seismicity, our classic Wadati-Benioff zone earthquakes, right? These are taking place within the downgoing oceanic lithosphere as a result of the volume change associated with those dehydration reactions. Now, if that fluid can actually escape from the downgoing crust, it can be reflected in different processes depending on the depth at which it's released. The depths we're interested in today is this depth range between about 20 and 50 kilometers depth, where we see this transitional behavior that we call non-volcanic tremor and episodic slow slip. So this kind of lies between our seismogenic portion of our plate interface, so where we have our great earthquakes and subduction zones, and the stable sliding portion further down dip. We think this is enabled by the buildup of very high pore fluid pressures near the plate interface to enable this kind of slip behavior. So if you're not familiar with this process, this episodic slow slip and non-volcanic tremor, really quickly outline what we see associated with these events. So let's put some co-located geodetic and seismic station out in our forearc immediately above the location of the plate interface that undergoes these processes. If we look at geodetic data associated with this station, we see something that looks very much like the seismic cycle. So during these periods, we have kind of landward motion of our geodetic station being recorded, telling us that we're accumulating stress on our plate interface, and that is straining the overriding plate. And then every once in a while, we'll see a reversal of this geodetic signature telling us that we're releasing stress along the interface. Now, in most subduction systems, if we see a signal like this, it's associated with a megathrust earthquake, an earthquake taking place along our seismogenic portion of our plate boundary. Right? This takes place over a period of seconds and releases a lot of seismic energy as a result. But in these slow slip events, this process where we're releasing stress takes a much longer time period. Rather than seconds, in Cascadia, it takes periods of weeks, and other subduction margins that have this behavior, it can be even longer, months to maybe even years. Okay, so that's the geodetic signature that we see associated with these. That's what we call slow slip. But these are accompanied by a seismic phenomenon as well, which we call a non-volcanic tremor. Okay, this is, instead of being an impulsive arrival like we get from our earthquakes, it's basically an increase in the background level of noise that we see on our seismic instrumentation in the region. Okay, that's kind of what it looks like. But this increase in noise is contemporaneous with this geodetic motion and is seen over kind of a regional array of stations. Okay, so it's not a kind of site response. It is clearly tied to some physical process that's happening in the margin. So that's our seismic signature, our non-volcanic tremor. So combining these two in Cascadia, we get our episodic tremor and slip events. Now, of course, we can release these fluids at greater depths as well. If it's in the cold portion of our mantle wedge, this will lead to serpentinization the mantle wedge, it'll lead to flux melting and eventually come out as volcanism in our magmatic arc, potentially. I'm not going to talk about these two in this talk. There's clear lateral variations in these as well. We are working on the volcano aspect, but this is kind of complicated by back arc tectonics that are affecting Cascadia as well, so it can't be purely tied to subduction zone processes. So we'll just focus on these seismogenic phenomenon. And I would say this is a nice 2D conceptualization of what a particularly warm subduction margin looks like. But of course, the real Earth is much more complicated than that, which is great for those of us that study these systems for job security's sake. So if we look at intraslab seismicity along the margin, we see that it's highly localized to northern and southern Cascadia. All right, so that correlates with our distribution of non-volcanic tremor along the margin, where we have high intraslab seismicity. We also have higher rates of non-volcanic tremor. We also have shorter recurrence intervals for our slow slip events, that geodetic signature associated with this process. And maybe it's not so surprising that these correlate, right? These are both fluid-mediated processes. But it's not so clear why this would correlate with something like Bouguer gravity, right? So Bouguer gravity tells us about mass deficits sub-sea level, low Bouguer gravity anomalies in northern and southern Cascadia. Now, generally, when we see these in mountain belts, we attribute that to differences in something like crustal thickness. But here, the slab is basically the same depth beneath the entire margin. So this likely tells us something about crustal density differences in the region. Not clear why crustal density would correlate with these interplate or intraplate phenomenon. We also see a correlation with uplift rates along the margin. So this is from GPS data, tide gauges, leveling surveys, that's the dots. The background is a predicted uplift from a plate locking model, so we can get kind of a more regional extent. But we see northern and southern Cascadia characterized by higher uplift rates than central Cascadia. And of course, if there's some anelastic component to our uplift, that's going to lead to the building of topography over time. Fundamental question we're interested in is figuring out how these different observations are linked. To do that, we need to understand what the subsurface structure looks like. And this is not an easy task in these Forearc domains. First thing we have is we have very large changes in seismic properties laterally. We know that crustal material has the widest range of seismic properties of any layer on Earth. So we need lateral resolution that can recover those changes in seismic properties. But we also have a lot of large vertical velocity changes as well. For instance, globally, we have our MOHO, our crust mantle transition. It's pretty clear in many places, but in forearcs, it's complicated by things like the serpentinized mantle forearc, which has velocities that are very similar to what we see in our overriding plate. We also have areas where there's no overriding plate mantle, so it's crust on top of oceanic crust on top of that mantle lithosphere, so large changes in velocity properties vertically potentially there. And of course, if there's fluids in these systems, that's going to complicate our seismic images as well. So to do this, we're going to use two complementary data sets. The first is using surface waves derived from ambient noise measurements. These are Rayleigh waves more specifically. And the benefit of using this data set is it's sensitive to the absolute shear wave velocities in the Earth where these waves are propagating. So for instance, we see, and this is good because if we're interested in investigating an area where we think fluids are playing a role, then it should really get highlighted by these shear wave velocities. Shear wave velocities are more sensitive to fluids than P waves, for example. Now, the shortcoming of this method is it has very broad sensitivities with respect to depth. So for instance, an 8-second Rayleigh wave phase velocity, so we measure these as a function of their period, is sensitive to the shear wave velocities between about 5 and 30 kilometers depth, basically as defined by the sensitivity kernel or the weighted average of velocities defined by that kernel. Okay, so if there's a discontinuity somewhere in that depth range, this data set's not going to see it. We can try to help mitigate that by adding measurements at more periods, which we always do. But you can see that these things, sensitivities are just so broad that they're not going to constrain our depths to boundaries well. For instance, our MOHO here, a wave that's sensitive to that is also sensitive to plus or minus 30 kilometers on either side of this discontinuity. But we can pair this with receiver functions, a data set that's extremely sensitive to velocity contrast. In particular, we're using P-wave radial receiver functions in this study, but you can see the response of a to that same velocity model. We see a really nice positive amplitude peak whose amplitude corresponds to the magnitude of the velocity change across that boundary. If these are velocity increases, we'll have a positive polarity. They can also recover velocity decreases with depth. It'll be a negative polarity. The shortcoming of this technique, though, is it's not sensitive to the absolute velocities on either side of the boundaries, only the relative velocity change across that boundary. But you can see that the strength of one of these is the weakness of the other. So what that means is we can combine these in a joint inversion approach to create a 3D shear wave velocity model that's fundamentally only driven by the data. And that's really important because a lot of times in inverse theory, what we get out is very dependent on the assumptions that we make when we're going in. So for instance, if you use only Rayleigh waves to try to solve for structure, you're going to need to impose something like crustal thickness so that you have a velocity jump at the right domain. So you can recover basically geologically realistic velocity structure. Now, if that assumption on crustal thickness is wrong, that's going to propagate into your final model, and you could end up with some erroneous results due to that. But combining these data sets, we don't have to do that. So let me show you conceptually how we build this model. First thing we do is we create a 3D model of our discontinuity structure throughout our study area. This is a cross-section along a portion of the Forearc in Cascadia. Where isn't important right now, we'll come back to this. But what's important is we can compare these discontinuity models, let's say from our receiver functions, which tell us about where velocity increases or decreases and by how much. We can benchmark these with independent estimates of surfaces, so independent estimates of crustal thickness or the location of our slab. And we see pretty good agreement. For instance, we see this nice positive peak that corresponds with pre-existing estimates for crustal thickness. We also see this positive peak that dips and comes in just a little bit later than where we expect the top of our slab to be. That's what we would generally interpret as the MOHO of our downgoing oceanic lithosphere. So we can combine this with our ambient noise derived Rayleigh wave dispersion data along the same cross-section, plug it into a starting model that's a simple half space, so 4.5 kilometers per second, through the entirety of the model, discretize into 1 kilometer thick layers because it's about the theoretical resolution of the receiver functions we're looking at. And what's really important to note is the starting model has no knowledge of this discontinuity structure ahead of time. And then we simultaneously fit these data sets and we get what we expect to get for a subduction zone, something that looks very much like a subduction zone, even though our starting model has no context of the tectonic environment that we're in. Okay, so we see these yellow colors that are consistent with crystalline crustal materials, transitioning to these blue colors consistent with what we expect for mantle peridotite at those pre-existing estimates of where the crust mantle transition should be. So we're recovering that really well without having to bake in that structure. We also see this dipping fast velocity body associated with our downgoing oceanic lithosphere. So this starting model, right, no tectonic context, it might as well think we're in the middle of the North American craton where I am at Purdue University. We could use this model and apply it to this location and we'll recover a structure consistent with the craton, right? So using this model is powerful and limiting our assumptions that we have to make in recovered structure. Okay, so now let's look at regions where we have particularly high amounts of non-volcanic tremor and compare that with our velocity structure that we resolve. So here's a section through the northern portion of Cascadia, through the Olympic Mountains, Puget Lowlands, just north of the latitude of Seattle. And the most striking feature we see in this cross-section is this very low velocity zone that lies in the lower crust of our overriding plate. It parallels our downgoing oceanic slab surface and spatially is located very well with the projection of non-volcanic tremor onto this line. These velocities get really slow, about 2.8 kilometers per second, which is really too slow to be attributed to crystalline crustal material and likely necessitates the presence of fluids. This was validated later by some magnetotelluric modeling done by Gary Egbert and his this very low velocity zone, we also have very low resistivities or high conductivities, indicative of fluids being present at this location, right? Again, spatially coincident with that distribution of non-volcanic tremor. So what does the internal structure of this low velocity, high conductivity region look like? Well, in this portion of the margin, there's been some really nice marine reflection data that's imaged this low velocity zone before. It's known as the E layer in most of the Cascadia literature, and it's characterized by this kind of 10-kilometer thick, highly internally reflective package of low velocities. So note that this color palette's flipped compared to ours. This is just kind of the standard for a lot of active source imaging. So yellow is slower than the reds on either side here. So this is our low velocity zone that we see in our images. And they interpreted this as underthrusting sediments below the margin. Now, of course, given the pressure temperature conditions we're at, these are going to be metamorphosed. And given the velocities and conductivity we see, these likely have fluid within them. Also try to get an idea of the composition of this material by comparing with some ideas on the structural fabrics at depth. So this is some work by my graduate student, Manuela Hurtado. It's currently in prep. This is radial anisotropy. We won't talk about how we get this, but the important thing to note is if you're blue, you're dominated by horizontal fabrics. If you're red, you're dominated by vertical fabrics. We see, corresponding with our low velocities, that we have very high anisotropy, telling us that there's horizontal fabrics here. Now we can take the magnitude of these horizontal of this anisotropy, compare it with what we might expect in a subduction system, kind of our basaltic rocks and sedimentary protoliths, variably metamorphosed. And what we see is really the only rocks that are consistent with this level of anisotropy is likely our metasedimentary rocks. We're likely at green schist facies, so that kind of puts us in this quartz mica schist range. So we think that this lower crustal, low velocity zone likely represents sedimentary material at depth consistent with those reflection images. Okay, so we can look at our other region of very high non-volcanic tremor density. We see basically the same structure, very low velocities in the lower crust of the overriding plate that spatially are coincident with the distribution of non-volcanic tremor. Now remember that that tremor is also occurring at the plate interface, so right below these low velocity zones. We project it onto the surface because we're not good at locating these as a function of depth, but we do infer they're occurring at that plate interface. We also have done a study from master's thesis of Brandon Herr, who's now a PhD student at Rice University, working with Brandon Schmant. But in his master's thesis that we're trying to get out now, we see the same structure as we see below Northern Cascadia, very high magnitudes of horizontal fabrics consistent with kind of a quartz mica schist lower crust. So this is a 3D model. We can look at it in map view as well. We see in areas that have high non-volcanic tremor density, the average velocity of the lower crust is quite low. Basically anything yellow and warmer might need the presence of fluids to get those velocities. We can also look at the thickness of these low velocity zones, and then we see that they're really thick, about 10 kilometers or so in many portions of the margin. So we would interpret that in northern and southern Cascadia, we have a lower crust composed of sedimentary material that's been underthrust beneath the margin and is being infiltrated by the fluids that are causing non-volcanic tremor. Now I want to do full disclosure. I'll show you a cross-section through this area that has limited non-volcanic tremor and no evidence of large low velocity zones at depth here. Here's a cross section through that area. Basically what we see is velocities consistent with the Silesia terrain or gabbros plate interface. So really no evidence for significant underthrust sediments in this portion of the margin. So we can put all three of these together to kind of get a conceptual knowledge of how things vary from north to south. And we can get a spatial view, a spatial kind of map view idea of this as well by comparing the thickness of those low velocity zones with the Bouguer gravity that we see along the forearc, where we have these very thick low velocity zones. Our Bouguer gravity is relatively low, right? Telling us that we have lower density material comprising the forearc in northern and southern have Silesia extending down to the plate interface. Okay, so it seems like non-volcanic tremor, which we can use as a proxy for the presence of fluid at the plate interface, correlates with these regions of underplated sediments, and the fluids that are causing tremor are able to infiltrate into these underthrust sediments to be manifest as the low velocity zones that we see. These low velocity zones are likely sedimentary in composition, which is reflected in the Bouguer gravity signatures that we see along the margin. Now, ultimately, we need to come back and tie this with our source of fluids, right? What is happening in the downgoing plate, and how are we bringing these fluids to actually affect our seismogenic processes, which is reflected in these other characteristics. So we kind of have two end-member hypotheses we can work with here. One is that intraslab seismicity reflects variable hydration in the downgoing plate. So in northern and southern Cascadia, right, the Juan de Fuca plate prior to subduction underwent a lot of deformation and was more hydrated than the lithosphere that subducts below central Cascadia today. So this is going to be primarily controlled by deformation that occurs prior to the subduction of our oceanic lithosphere. So we can try to look at some proxies for deformation today and see if we can kind of project those down dip to match the intraslab seismicity that we see. The first thing we can do is just plot earthquakes in the offshore region. We do see that the Gorda segment of the Juan de Fuca plate has a lot of intraplate seismicity. Now, if the seismicity is creating faults that are acting as permeable pathways for fluids, this would imply that Gorda is much more hydrated than the central Juan de Fuca plate. And maybe that fits with what's happening along southern Cascadia, where we have these higher rates of fluid-mediated seismogenesis compared to central Cascadia. But it doesn't seem to correlate very well with what's happening further to the north, our other region of high intraslab seismicity. This was complicated even more by the deployment of the Cascadia Initiative Ocean Bottom Seismometer Array that occurred from about 2011 to 2015, blanketing the Juan de Fuca plate with these OBS instruments. During at least this period, the seismicity rates weren't that different between central Cascadia and what we saw in the Gorda. So what that might mean is that previous picture I showed you, which is just the USGS catalog, didn't quite have the recording sensitivity necessary to constrain these intraplate earthquakes within the central Juan de Fuca. You can see this is a little further from the coastline. Period, there was a lot less seismometers and kind of particularly in coastal Oregon compared to what we had in Northern California, where these events are a little closer. So maybe there's some catalog bias there, but at least over this time period when Cascadia Initiative was deployed, we don't see particularly strong evidence of different seismicity rates in these areas, although I will say that earthquakes tend to be larger further to the south. We also can look at some seismic reflection, one line in central Cascadia, one further to the north. And we see that the deformation in the central Juan de Fuca plate is actually much more pervasive than what we see subducting below the north. Right? This is the area that's going into this region of pretty negligible intraslab seismicity versus our higher amounts of intraslab seismicity. And what we see in central Cascadia is these very deep-seated reflective discontinuities that are interpreted as moho busting faults, basically. Okay, so again, potential pathways for fluids, then if fluids can reach these faults and percolate into our downgoing oceanic lithosphere, if they get into the mantle, they're going to be able to hydrate the downgoing plate much more than if they're just constrained to the crust, as we see for northern Cascadia. Right, so our mafic rocks, our gabbros and basalts, they can hold maybe 2 weight% water if fully hydrated, but our mantle peridotite, if we serpentinize that, can hold up to 12 weight% water. So we can take down a lot more fluid if we can get that water down to the mantle peridotites. Okay, so this is again opposite of what we'd expect to see if we project this down dip. We can also look at P-N velocities. So these are refracted P waves in the uppermost mantle of the Juan de Fuca plate. Okay, so these are going to tell us about mantle hydration. What we see in this study is that in the Gorda segment, where we seem to have more seismicity, we actually seem to have a much drier mantle. So velocities that we recover are consistent with what we'd predict for half-space cooling of oceanic lithosphere until we get near the Mendocino fracture zone to the south. Of course, this is a plate boundary. We expect this to be more altered and more permeable, allowing for fluids. But that's not the majority of the Gorda segment. But when we look at the central Juan de Fuca plate, we see a pretty big deviation from what we'd predict for dry mantle versus our observations, telling us that this should be kind of more hydrated than what's subducting in the southern portion of Cascadia, where we have the most intraslab seismicity. And last thing I'll show you is a refraction line from about central to northern Cascadia. Here what we see is that central Cascadia again appears more hydrated, lower velocities in the oceanic crust in central compared to the north. This was directly interpreted as evidence for hydration by this study. So what I'd really like to do here is put a big X through this hypothesis, right? Variable hydration does not seem to be able to tell us much about what's happening further down dip in the subduction zone. I'll put a question mark on here for now because there's a lot of research being done in the offshore portions of Cascadia right now, particularly the KC21 data sets, a lot of reflection lines as well as OBS data, whose specific goal is to try to map out deformation in the downgoing plate prior to subduction, as well as structures in our accretionary wedge. Maybe they'll find something different, but this is still quite a bit of evidence you have to overcome if you want to call on variable hydration as being the dominant control of what we see further down dip in the subduction zone. So now let's go to our other end-member hypothesis, and that is that we can take down a uniformly hydrated slab into the subduction zone. Okay, so that means that what we're seeing reflected in intraslab seismicity is not related to hydration, but rather related to where these fluids are actually able to escape from the downgoing plate. Okay, so this would be primarily driven by permeability that's created within our downgoing plate post-subduction. Okay, uniformly hydrated, where this is looking at where fluids might be released rather than where the volumes that we're taking down. Okay, so what can we look at as a proxy for this? Of course, seismicity is kind of a first order one, right? Every time an earthquake happens, we might be able to create at least a transiently permeable fluid pathway. If fluids are present, they will take that pathway and escape from the downgoing plate and be reflected in these shallower seismogenic processes. We can also use these hypocenters to tell us about the morphology of the downgoing plate as well. When we do that, we see that northern and southern Cascadia have a much more deformed slab top. We can quantify this through a slab curvature. Basically, what we're looking at here is how concave down or convex down the top of the slab is. Reds would tell us that the top of that slab is concave downward. So our areas that we have concave down surfaces to our slab are where we have higher amounts of intraslab seismicity. Now, of course, we know from intro geophysics that if we take some elastic beam and we bend that beam, we put the top of that beam closer to tensile failure. And we know that rocks in tension fail at lower differential stresses than rocks in compression. So what we might be seeing reflected in this seismicity is actually telling us where the slab top is more easily or more readily able to fail and release these fluids. But now, of course, we have to think about what controls slab morphology along the Cascadia margin. There's been some nice mantle tomographic imaging done in this region, showing that in our subslab domains, we see these very low velocities in the uppermost mantle below our slab. So here's our subducting Juan de Fuca slab going off to the east. These are subslab low velocity zones that have been interpreted as these buoyancy anomalies. So what they would be doing is basically trying to rise up. They're going to hit that subducting slab, and then they're going to bend that slab surface to lead to that concave down curvature we see associated with these regions. Okay, so now let's bring all this together. So we have our subslab low velocity zones controlling our slab morphology. You can see decreased dips associated with these, as well as increased curvature as we come off the edge of the slow velocity zones. These puts the slab surface closer to tensile failure, which is reflected in our intraslab seismicity. The seismicity leads to permeable pathways for fluids that are present to escape. They can concentrate at the plate interface and be reflected in that distribution of non-volcanic tremor and slow slip that we see. These fluids are then able to infiltrate into those underthrust sedimentary packages, which are reflected in our Bouguer gravity anomalies. Okay, so I think this gives us a good idea of what's happening in the subsurface below Cascadia. But how can we link this to geological observables that we can go out into the field and see and potentially do some hypotheses tests on? So one thing that is that we've had to think about and how we get these, well, let me rephrase this. We have to figure out how we make 10-kilometer thick zones of low velocities in the. We're not taking down 10-kilometer thick packages of sedimentary rocks at our trench today. So these things have to represent some kind of time integrated process over which we can accumulate this material at depth. Okay, one way that we can build these up that's had some really nice thermomechanical modeling done on it recently is the process of basal accretion, okay, the transference of material from downgoing to overriding plate. So here's kind of our setup here. We have our subducting oceanic crust. It has its pelagic sediments and dark orange, our terrigenous sediments, and light orange. We have our basaltic oceanic crust in dark green, gabbro, light green, and then our oceanic lithosphere. What we see is that when we model the basal accretion process, we can slice off little bits of our downgoing plate. These darks represent basaltic units that have been sliced off. These oranges represent dominantly sedimentary material. And this drives uplift and exhumation immediately above the locus of basal accretion at depth. This also leads to some structures that this also predicts some structures that we can look for in the field, things like domal shapes or anticlinal structures in these subduction forearc domains. So let's put this in the context of our shear wave velocity images. We have our low velocity zone in Cascadia. We can put a box around here to scale that to this thermomechanical model, right? We think that this is dominantly composed of sedimentary material at this portion of the margin. Can we see geologic evidence of this process occurring in the Cascadia Forearc? I would say we can in both regions where we see these thick low velocity zones. For instance, in the north, we can look at the Olympic Mountains and we see very interestingly, based on low temperature thermochronological data, this kind of bullseye shape to exhumation, long-term exhumation since about mid-Miocene times or 15 million years or so. So we can digitize this bullseye shape, which is what would be predicted from this modeling. We can overlay it on our velocity model, and we see a pretty good match with where we see low velocities in these areas of increased exhumation rates as well as topography along the margin. We can also compare this in southern Cascadia to this interesting tectonic window called the Condry Mountain. So these are kind of blue schist to green schist facies rocks that have been explicitly interpreted by Carolyn Tewksbury Chrisley and Whitney Baer and others, as well as people before them back in the 80s, as these underplated sedimentary rocks that are being exhumed, and they've come up all the way to the surface through our Klamath Mountain terrain. You can see the foliations associated with this are dominantly kind of spreading out from the central portion of this tectonic window. So making this predicted pattern consistent with that thermomechanical modeling. Okay, so it seems like the basal accretion process itself is what can lead to these thick packages of sediments that are accumulating below the forearc. Of course, basal accretion is by definition an inelastic process, so it's going to lead to the building, or it's going to lead to uplift that is unrecoverable during the seismic cycle and therefore build variations in topography over time. Okay, but now we have to come back and link this to the fluid in the margin, right? How are fluids potentially affecting this basal accretion process and therefore leading to uplift and exhumation that we see? So we know from this modeling, as well as maybe intuitively if you work on rheology, that basal accretion is going to be linked to the rheology of the materials at the plate interface. That's going to be tied to the temperature at the plate interface, the composition of the material at the plate interface, and importantly, the presence of fluids at these depths. Okay, so if we have fluids present, we think that this actually makes basal accretion much more efficient because it functionally weakens, or I should say, it allows this material to fail more easily, detach from the downgoing plate. It's low density, so it doesn't want to get subducted if it can help it, and transfer to being part of that overriding plate. Okay, so we can bring this all together now. So our subslab buoyancy anomalies modulate our slab morphology that controls the distribution of intraslab seismicity that we see along the margin. This tells us about where we're releasing fluids, particularly in high amounts, which we see reflected in tremor at the plate interface. These fluids enable more efficient basal accretion to happen where they're more readily available, leading to the buildup of these thick, low velocity zones in northern and southern Cascadia. These are dominantly sedimentary in composition, which is reflected in the Bouguer gravity field. And the basal accretion process itself leads to or contributes to uplift as well as the building of differential topography over geologic timescales. Okay, so now I think we have a decent sense of what's happening along the Cascadia margin, what could be controlling all the lateral variability that we see. But is this applicable to any other subduction margin globally? So we know Cascadia is not the only location that has these elevated forearc topographic. We see it in Alaska, also see it hinted at in northern and central Chile as well. So we can look at the subsurface structure in these domains to see if we also have evidence for basal accretion. Another thing to keep in mind is at least some of these margins also have this deep non-volcanic tremor, right? Telling us that fluid is readily available at depths that could lead to this process being more efficient. So the most correlative image we see is in Alaska, where we have our Chugach terrain. It's underlain by something that looks very much like what we see in Cascadia. So this is a model by Kevin Ward and Fan-Chi Lin, also a joint inversion of receiver functions and surface waves. So we expect these to look very similar if they're recovering similar subsurface features, right? So this area high Chugach mountains that are undergoing really rapid exhumation, like 4 millimeters a year, are underlain by one of these very low velocity zones in the lower crust. Might see it hinted at in central Chile. We kind of see a decrease in our velocity contours associated with our subducting plate. We see it beautifully reflected in reflection imaging. Yeah, sorry for that. Didn't mean to repeat those. In reflection imaging in Nankai, so these really nice duplex structures interpreted as basally accreted sediments. It's shallower depths. So interesting to know if this is completely analogous to what we're seeing. Maybe this extends to greater depths as well. And it's also been interpreted to occur beneath the Rurukumura Peninsula in New Zealand based on seismic imaging and low temperature thermochronology. Okay, now lastly, I want to talk about what we're doing moving forward here. So I'm part of the Cascadia Region Earthquake Science Center, or Crescent, whose goal it is to better understand the physical processes that drive Cascadia subduction. I'm involved in this because of this previous work we've done on the Cascadia margin, but really importantly, we want to start doing this in the context of natural hazards and hazard mitigation in Cascadia. So I'm happy to say that at least at the beginning of Crescent, I was the only university located within the craton of North America studying these subduction zone systems. We've expanded since then through seed funding and other personnel to have more universities in the Midwest here. And we're always looking to bring more people into this community. I think we currently have seed grant opportunities out. So if you're interested in expanding into Cascadia research, please do look into that. Crescent's divided into 5 different working groups. I'm part of the community velocity model, as you might expect, given my background and expertise. And our charge is to create a new seismic velocity model that can better inform not only the physical processes occurring along the margin, but can also be leveraged for things like constraining elastic parameters and waveform simulations that will be used by our dynamic rupture simulation group, as well as our geodetic modeling and seismicity groups. And another thing that we might be able to do is help constrain subsurface faulting extents. If you've been to the Pacific Northwest, you know that many portions are heavily vegetated, making it difficult to do geologic mapping. But with the surface constraints that we do have for faulting, we might be able to see the extent of these faults in the subsurface as well. This is the group that's currently part of the Cascadia, the CVM group, the Community Velocity Model group. I want to highlight Ben He, who was a postdoc here at Purdue as part of the Crescent Initiative and has now moved to finish his second year of his postdoc at University of Oregon. He's leveraged a lot of new data that's come out since I published some of these velocity models to create a new velocity model. It largely appears similar to what we've published in the past, which is good. But one really important thing to remember is because we're doing this in the context of hazard mitigation, we also need to know our uncertainties. So Ben has been using approaches to these joint inversions so that we can highlight not only what the structure is, but how well we know that structure, which is important for estimating things like ground shaking that propagates through this foundational model. So with that, I'd like to thank you very much for your attention.
Thank you, John. Thank you very much. I invite everyone here to, yes, exactly, use your hand clap emojis to thank John for taking the time to share his work with us today. Anybody has any question, please use the Q&A feature. Doesn't seem like we have any questions from the attendees.
So it must have just been so clear.
It was so clear, John. Yes. We have one question. Do you want to read it or?
Sure, yeah. Thanks, Elizabeth. Are these models incorporated into a Crescent CVM? So if you go to the Crescent website, you will see these models uploaded to our CVM web viewer. This model isn't directly incorporated because we want the uncertainty. All the data is incorporated, though, in the model that Ben is working on. So this model that he's created incorporates all of the data that went into our 2018 and 2021 models, plus a huge expansion of data that's occurred since about 2020, thanks to the Pacific Northwest Seismic Network. So we've increased the amount of data that's going into this by quite a bit. I forgot to mention this is in revision, and we're hoping to get those submitted very soon. So keep your eye out. Hopefully, this comes out pretty soon.
Thanks. We have another question from Brianna. You want to read it?
Sure, yeah. Brianna, at some point, would velocity models be available that could be used to improve earthquake locations based on direct phase arrivals? So this is something that particularly the CSSS C3S group is working on, coupling seismicity and slow slip. So they're trying to incorporate these 3D models into earthquake location algorithms. I'm really curious to see how that works. A lot of times we locate earthquakes using earthquake arrival times, right? Whereas in this model that we're creating, we're using passive imaging techniques to create a 3D model, and then we'll see how that does at locating the earthquakes. So I think this is like a really interesting way forward. Like, how can we create regional models with passive techniques that can be applied to local seismicity?
Thanks for your question, Brianna. We have a question from Tian-san. Hi, Tian. John, thanks for the great talk. What about mafic underplating? Can we tell what's being underplated is meta sediments or meta basalt?
Yeah, good question. I think the meta basalts, below Vancouver Island, work that's been happening up with Michael Bostock's group for many years has interpreted that this underplating is predominantly composed of meta basalts, so oceanic crystalline crust. I think it's really hard to tell the difference. I would say that the velocities that we see below the Olympics and below the a bit lower than what is seen beneath Vancouver Island. And we allude to this in the 2021 paper. There could be the possibility that this underplating is occurring everywhere along the margin. And really, we're only seeing it well with our imaging techniques in areas where it's particularly slow because it's metasedimentary. But we do see these low velocity zones below Vancouver Island. They're just not quite as slow. So one thing that I'm really interested in looking at in the future, particularly as Ben finishes up his the initial CVM model, is how the velocities, given the same technique, compare below the Olympic Mountains versus Vancouver Island.
Thanks, John. Thanks, Tian, for your question. John, would you like to address Amberly's question in the chat?
Yeah. Do you have any idea why there are two buoyant regions? Yeah. So that work, I think, interprets that these are close to, one is due to it being close to the slab edge. Let me see if I can find it over here. Sorry, take forever here. One is close to the slab edge in southern Cascadia. The other one might be related to some sort of fracture kind of near, I think, the Juan de Fuca and Explorer plate junction, or some sort of little plume that's closer to the ridge getting dragged into the subduction zone. But I'd refer you to the Bodmer 2018 paper to get their ultimate interpretation of where these things are coming from.
Thanks for your question, Amberly. John, we have a question from Will in the Q&A feature. Will says, great talk, exclamation point. If you could do seismic imaging further away from the subduction zone beneath the ocean, are there features that you might look for in the models that might support one of these hypotheses or another?
Yeah, I think with the data sets we're using, we can certainly be quite sensitive to offshore upper mantle structure. The ambient noise method, when you have as thin of a crust as you do offshore, right, 6 kilometers or so, we're really not going to be able to use that data to tell us about, let's say, crustal features as much. But we could look for upper mantle hydration differences from offshore ambient noise measurements. I'm not sure if anyone has specifically focused on that, although there's quite a few papers that look at the offshore structure using OBS ambient noise. But that could be a place we could look is can we constrain and with what confidence those velocities in the uppermost mantle to look for variability in hydration prior to subduction? Good question.
Okay. Well, it seems like we no longer have any question. Giving just a couple seconds. Anybody else? Okay. No. Well, if there are no more questions, then I would like to thank you again, John, for taking the time to join us and sharing your work. Thank you all for taking the time to join us today. Quick reminder that this webinar was recorded and will be available soon on our SZ4D YouTube channel. Our next webinar will take place in May, and we will announce the details in the listserv. So on that note, I hope that you all enjoy your day, and please join us for our next webinar.
Yeah, thank you everyone
John.
for coming.
Thanks, everyone. Bye.